Tonight, we drift into the silent ocean of ice that encircles Saturn. It is not just a structure, but an endless world of frozen particles, floating in the quiet vacuum. Welcome to the Orbit for Sleep channel. Let gravity guide our journey and drift gently toward sleep. You move through a quiet region of space where the light changes in a subtle way. The familiar darkness around Saturn shifts into a pale, reflective field that extends across hundreds of thousands of kilometers. The transition resembles stepping from a dim hallway into a room filled with soft, suspended dust. Each piece of ice follows a clear and predictable orbit, and their collective motion forms a stable structure that behaves more like a wide, gently turning disk than a cloud. The first impression comes from the enormous scale paired with unexpected thinness. The rings spread outward for a distance similar to the span between Earth and the Moon, yet the vertical thickness compares to the height of a city block. This unusual ratio produces a sense of entering a flat plane suspended in space. The orientation of the particles creates a layered environment that remains nearly transparent at close range. This transparency contrasts with the bright appearance seen from a distance, where reflected sunlight makes the rings appear solid. As you continue inward, the texture of the environment becomes clearer. Most particles consist of nearly pure water ice. Their surfaces scatter sunlight in a way similar to frost on a window during a cold morning. The brightness varies depending on particle size. Small grains reflect light uniformly, and larger fragments produce sharper flashes. A person standing near them would see continuous movement without sound. The absence of air removes any acoustic cues, creating an environment defined by motion but not by noise. The structure of the rings began forming long before humans studied them. Early observations in the 17th century produced many interpretations, including the idea that Saturn possessed two large handles. More precise telescopes later revealed the flat disk shape. A spacecraft entered the Saturn system in the late 20th century. Direct measurements confirmed details about particle composition, density, and orbital behavior. These findings explained why the rings remain stable. Each particle orbits according to a balance between Saturn's gravity and its own forward motion, the same balance that keeps Earth circling the Sunday. A useful comparison comes from seeing dust move inside a sunbeam in a quiet room. The dust pieces drift independently, yet the beam outlines a consistent shape. Saturn's rings follow a similar principle on a vast scale. Instead of drifting randomly, each particle travels along a path determined by gravitational equations. Local interactions cause slow adjustments. When two fragments collide, the impact resembles tapping ice cubes together. The low relative speed allows them to maintain the disk's organized structure. The environment also carries signs of long-term evolution. Small meteoroids occasionally strike the rings, adding darker material that gradually alters their brightness. Over millions of years, this contamination may reduce the whiteness visible today. The rate of change gives scientists clues about the ring's age. Some evidence points toward the rings forming during the 20th century of Saturn's history, while other models suggest a more recent origin created by the breakup of an icy moon. The moment you enter the rings reveals a balance of order and motion. Each particle remains part of a complex system that reflects the history of Saturn's environment. The structure extends far beyond personal experience, yet remains built from simple physical rules. The scale encourages a slower rhythm, allowing the mind to follow the steady paths of ice as they orbit in silence. Saturn's rings form a broad structure made primarily of water ice. The composition becomes clear when sunlight reflects off the particles, creating a brightness similar to the surface of frozen lakes on Earth. Most fragments range from the size of fine grains to the size of household objects. Larger pieces, although less common, still follow the same orbital pattern. Their distribution creates a system that appears smooth from far away, yet contains many detailed variations when viewed up close. The particles maintain predictable behavior because each one orbits Saturn according to well-defined gravitational rules. Water ice forms the majority of the material, and this purity explains the ring's pale color. A small fraction of the mass includes rocky debris. This material likely originated from ancient collisions involving moons or comets. When these objects broke apart, the fragments spread across a stable region around Saturn, becoming incorporated into the ring system. A comparison with snow on the ground helps explain how ice particles of different sizes interact with sunlight. Powdery snow reflects light evenly, and the surface looks smooth. Coarser snow creates brighter, sharper glints. Saturn's rings display the same traits. Fine particles produce a soft glow, while larger fragments generate distinct reflections that change as they move. Variations in brightness across the rings reveal differences in particle size and concentration. The ring's composition also reflects the physical history of Saturn's environment. Spacecraft measurements during the late 20th century confirmed that the rings contain extremely little organic material. The lack of heavy elements suggests the fragments did not form alongside Saturn in the early solar system. Instead, the evidence points toward the breakup of icy bodies that once orbited the planet. Their shattered remains spread across many orbits and gradually settled into the thin, wide disk seen today. Micrometeoroids play a steady role in modifying the rings. These tiny objects continually arrive from interplanetary space and strike the ice particles. Each impact adds darker dust to the system. Over long periods, this contamination reduces the ring's brightness and contributes to slow structural changes. The amount of accumulated material allows scientists to estimate the ring's age with reasonable accuracy. The composition of Saturn's rings creates an environment defined by clarity, reflectivity, and motion. Water ice forms the foundation, and small amounts of rock and dust provide additional texture. The result is a structure shaped by collisions, gravitational balance, and the long-term evolution of nearby moons and comets. Standing near the rings would reveal countless ice fragments moving in coordinated orbits, each one contributing to the overall appearance of a bright, thin plane that circles the planet. Saturn's rings produce a level of brightness that sets them apart from the rings of other planets. This brightness comes from the high concentration of water ice spread across the structures that circle the planet. Water ice reflects a large portion of incoming sunlight. The reflection creates a clear and pale surface similar to the appearance of freshly fallen snow on Earth. When large regions of this material exist together, the total reflected light becomes strong enough to be visible across vast distances in space. The purity of the ice plays a major role. Measurements from spacecraft during the late 20th century showed that Saturn's rings contain less dust and rocky debris than the darker rings of Jupiter or Uranus. Less contamination allows more sunlight to bounce directly off the ice. Even small differences in surface texture can change brightness. The ice particles in Saturn's rings often retain smooth or slightly rounded surfaces, and this enhances their reflective properties. The arrangement of the particles also contributes to the brightness. The rings stretch over a very wide area, forming an expansive disk with high surface coverage. The total number of particles involved means that even though the rings are thin, their combined surface reflects a significant amount of sunlight. A useful analogy comes from snow fields. A thin layer of snow still appears bright when sunlight strikes a large enough area. Saturn's rings function the same way, on a scale far beyond anything on Earth. The lack of heavy organic materials provides further clarity. When micrometeoroids collide with the rings, they deposit darker dust. Over millions of years, this contamination can reduce the brightness. The relatively low levels of accumulated dust suggest that the rings may not be extremely old. A younger system retains more of its natural reflectivity, which aligns with the high brightness observed today. The distance from the Sun shapes the visual effect as well. Saturn receives less sunlight than Earth, yet the rings remain visible because the ice reflects such a large fraction of the available light. The contrast between the rings and the darker background of space increases their apparent brightness. As Saturn moves through its orbit, the angle at which sunlight strikes the rings changes gradually. These seasonal shifts affect their appearance, but do not significantly reduce their reflective quality. Comparing Saturn's rings to those of other planets highlights the role of composition. Jupiter's rings consist mostly of dust, and dust absorbs more light than ice. Uranus and Neptune contain darker materials mixed into their ring systems. These differences explain why Saturn maintains the brightest and most visible rings in the solar system. The combination of pure ice, wide surface area, and limited contamination creates a structure that continues to reflect sunlight with remarkable clarity. Saturn's rings maintain their structure through a balance of gravitational pull and forward motion. Each particle of ice or rock orbits Saturn because it moves fast enough to avoid falling inward, yet not fast enough to escape the planet completely. This balance follows the same principle that keeps Earth in orbit around the Sunday. The motion forms a continuous path that repeats steadily, creating a stable system made from countless individual orbits. The gravitational field of Saturn provides the central force that organizes the rings. Larger particles, smaller grains, and fragments of varying sizes all respond to this force in predictable ways. Particles closer to Saturn travel at higher speeds. Those farther away move more slowly. These differences in speed prevent the ring system from turning into a single clump. Instead, the variation creates separate layers, each following its own orbit. A comparison can be made to cars traveling along multiple lanes on a highway. Faster cars move in the inner lanes, and slower ones stay farther out. As long as their speeds remain consistent, traffic flows smoothly. Collisions between particles play a role in shaping the system. Most collisions occur at low relative speeds, similar to the gentle contact of ice cubes shifting inside a container. These interactions help prolong particles into a thin disk, Over time, the ring material settles into an organized configuration where random vertical motion decreases and horizontal orbital motion dominates. This is why the rings remain flat instead of forming a spherical cloud. Saturn's moons contribute to the ring's stability. Some moons orbit just outside the ring system, and their gravity influences the edges. These moons are known as shepherd moons. Their gravitational pull gathers and confines particles, preventing them from spreading too far outward or collapsing inward. The effect resembles the way a moving object can guide loose grains into a narrow path. The moons maintain gaps, define boundaries, and create patterns within the rings. The rings do not collapse because the particles follow orbits that match the gravitational environment. Each fragment moves along a path that repeats with precision. The system appears delicate, but the underlying physics keeps it stable. Observations from spacecraft during the late 20th century confirm this behavior, showing that the rings behave as a collection of independent objects rather than a solid disk. Over long periods, external forces introduce slow changes. Micrometeoroid impacts, gravitational disturbances from moons, and interactions with Saturn's magnetic field gradually alter the rings. However, these effects unfold over vast timescales, allowing the structure to maintain its overall shape for millions of years. The combination of orbital mechanics, gentle collisions, and the guiding role of nearby moons explains why Saturn's rings remain intact and continue to circle the planet as a wide, thin, and stable system. The age of Saturn's rings remains one of the most studied questions in planetary science. Estimates arise from analyzing the amount of dust mixed into the ice, the brightness of the ring material, and the rate at which particles collide and evolve. Each approach points toward a system that has experienced significant change over time, revealing details about both the rings themselves and the history of Saturn's environment. Water ice forms the majority of the rings, and its brightness provides an early clue about their age. Pure ice reflects sunlight very efficiently. If the rings were extremely old, they would accumulate dark dust from micrometeoroids that constantly enter Saturn's neighborhood. This dust builds up slowly but steadily. Spacecraft measurements during the late 20th century found less contamination than expected for a structure billions of years old. This observation led to the proposal that the rings may be younger than Saturn, possibly forming within the last 100 million years. Another line of evidence comes from the distribution and behavior of particles. Collisions reshape the fragments over long periods. Small pieces grind into finer grains, and larger ones lose sharp edges. The current mix of particle sizes suggests a system that continues to evolve. Laboratory studies of ice under similar conditions show that these processes occur at predictable rates. When applied to the rings, the results imply a structure that has been active for a significant portion of Saturn's history, but may not date back to the earliest era of the solar system. A potential origin scenario involves the breakup of an icy moon. If a moon once moved too close to Saturn, tidal forces could have torn it apart. The fragments would then spread along stable orbits and gradually settle into a disk. The smoothness and coherence of the present rings match this possibility. A comparison can be made to a shattered object that continues to move in a circular pattern. Over time, the pieces distribute themselves evenly, creating a broad, thin structure. Direct observations of ring mass offer further insight. The total amount of material helps determine whether the rings have undergone steady erosion. If the rings were ancient, much of the ice would have been lost by now through processes such as sputtering, where charged particles remove molecules from the surface of the ice. Current mass measurements fall between the values predicted for a very old ring system and a relatively young one. This intermediate state supports the idea that the rings formed sometime after Saturn itself. Micrometeoroid impacts provide one of the clearest age indicators. The rate of incoming dust depends on the population of small objects in the region of space surrounding Saturn. By estimating how quickly dust accumulates, scientists can calculate how long it would take for the rings to darken to their current appearance. The results align with an age shorter than the age of the solar system. The rings may have formed during the later stages of planetary evolution, rather than during the earliest formation of Saturn. The age of Saturn's rings remains an active topic of study, shaped by multiple lines of evidence. Their brightness, particle distribution, mass, and contamination levels each offer clues. Together, these observations suggest a dynamic structure that has persisted for millions of years while continuing to evolve under Saturn's gravity and the constant flow of interplanetary material. The structure of Saturn's rings becomes more distinct when viewed as a set of separate regions. The A, B, and C rings form the primary components of the system, each with its own density, brightness, and particle distribution. These differences arise from variations in composition, orbital motion, and interactions with Saturn's moons. The result is a layered disk where each section contributes to the overall appearance while maintaining its own characteristics. The B ring occupies the central and brightest region. It contains the highest concentration of ice particles, creating a dense environment that reflects sunlight efficiently. The opacity of the B ring makes it difficult for light to pass through, even when observed at high resolution. The high density causes particles to collide frequently, although the collisions remain gentle due to the low relative speeds. These interactions help maintain the ring's thickness and contribute to its smooth appearance. The A ring lies outside the B ring. It contains fewer particles and displays a more open structure. The separation between the A and B rings includes the Cassini division, a wide gap shaped by gravitational interactions with one of Saturn's moons. The particles in the A ring continue to orbit in an organized pattern, but the lower density allows more sunlight to pass through. This creates a region with visible variations in brightness and texture. The C ring sits on the inner side of the B ring, closer to Saturn. It contains fewer particles and displays a semi-transparent quality. The reduced density allows sunlight to filter through, producing a dimmer and more diffuse appearance than the B ring. The C ring collects more dust from micrometeoroid impacts because it lies nearer to Saturn's gravitational influence. This dust contributes to its darker tone. A familiar example comes from examining layers of sediment in shallow water. Dense regions appear opaque, while areas with fewer particles allow light to penetrate. Saturn's rings behave in a similar way. The distribution of particles determines how much light reflects or passes through. The A, B, and C rings form a pattern that resembles a natural gradient created by differences in particle concentration. Spacecraft observations have revealed subtle variations within each ring. Waves, gaps, and spirals appear due to the gravitational influence of Saturn's moons. These features move through the ring material like ripples. Their presence helps scientists understand the mass and orbital properties of the particles. The A, B, and C rings form the foundation of Saturn's ring system, and their combined structure represents a balance between gravitational forces, particle density, and long-term evolution. The architecture of these rings demonstrates how a complex system can arise from simple physical processes. The arrangement of particles into layered sections reflects the dynamic environment around Saturn. Each region displays its own identity while contributing to the stability and appearance of the overall ring system. Between the bright A and B rings lies a wide gap known as the Cassini division. From a distance, this region appears almost empty, as if the ring system has been split into separate parts. Closer examination shows that the Cassini division still contains ring material, but at a much lower density than the surrounding regions. The origin of this gap comes from a combination of orbital mechanics and the influence of one of Saturn's moons. The Cassini division was first identified in the 17th century through telescopic observations. Early astronomers noticed that Saturn's rings seemed divided into distinct sections. This visual impression matched what later spacecraft confirmed from close range. The division is not a complete absence of material. Instead, it forms a region where particles are less common, and their orbits are strongly shaped by gravitational patterns. A key factor in the formation of the Cassini division is a resonance with the moon Mimas. Orbital resonance occurs when particles in the rings circle Saturn in a pattern that repeats in a simple ratio with the orbit of a moon. In the Cassini division, many particles would complete 2 orbits for every 1 orbit of Mimas. This repeated alignment allows the moon's gravitational pull to act on the particles in a consistent way over long periods. The repeated gravitational influence gradually changes the orbits of particles located in the resonance zone. Instead of remaining in stable circular paths, many particles are nudged into new orbits that move them out of the region. Over time, this process clears much of the material, leaving behind a gap with reduced density. The effect is similar to a child pushing a swing at the same point in each cycle. Each push adds energy, and the motion becomes larger and more noticeable. Within the Cassini division, smaller ringlets and structures still exist. These ringlets consist of particles that occupy orbits slightly offset from the strongest resonance, or that are temporarily stable due to local conditions. They form narrow bands that trace the underlying gravitational environment. Spacecraft images reveal fine patterns, including waves and subtle variations in brightness, all shaped by the same gravitational forces that created the division. An everyday analogy can be found in a rotating crowd moving around a circular track. If a regular disturbance occurs at specific intervals, such as a person gently guiding some participants toward the outer edge, gaps begin to appear where people are repeatedly redirected. The Cassini division reflects this type of organized clearing process on a planetary scale, driven not by physical barriers, but by the long-term effects of resonance. The existence of the Cassini division provides insight into how gravity structures material in disks around planets and stars. Similar resonance effects appear in asteroid belts and in the gaps of protoplanetary disks around young stars. The division within Saturn's rings stands as a clear example of how a single moon can shape the distribution of countless smaller particles through repeated, gentle gravitational interactions that gradually sculpt a large-scale pattern. Patterns of waves appear throughout Saturn's rings, forming ripples, spirals, and oscillations that extend across large regions. These structures arise from the gravitational influence of Saturn's moons. Each moon interacts with the ring particles at specific locations, creating disturbances that travel through the disk. The result is a set of wave patterns that resemble the behavior of ripples on the surface of water. Although the underlying physics is governed by orbital motion rather than fluid dynamics, orbital resonances serve as the foundation for many of these waves. When a ring particle completes its orbit in a simple ratio with the orbit of a moon, the gravitational pull from that moon occurs at the same point in each cycle. Over time, these repeated tugs change the particle's velocity slightly. The cumulative effect produces a region where particles shift in coordinated ways, forming organized wave-like structures. The amplitude and spacing of the waves depend on both the strength of the resonance and the distance from Saturn. Density waves arise when particles within a ring region compress and spread out in a repeating pattern. These waves resemble alternating bands of higher and lower particle concentration. Spacecraft images show sharp, tightly packed waves, as well as broader, more gentle patterns. The density waves move through the ring material as the particles respond to variations in gravitational force. The repeated pattern provides information about the mass and orbit of the moon responsible for generating the disturbance. Bending waves represent another form of structure influenced by the moons. Instead of forming horizontal patterns, bending waves tilt particles slightly above and below the main ring plane. These vertical oscillations travel outward from the point of disturbance. The effect can be compared to a sheet of fabric that rises and falls in a gentle wave. Although the ring system is extremely thin, these vertical motions become visible due to the collective movement of countless particles. An everyday example appears in the way crowds move at a sports event. If a section of people stands up in a coordinated pattern, a visible wave forms that travels through the stadium. Each individual acts independently, yet the overall pattern appears coherent. Saturn's ring waves follow a similar principle. The gravitational influence of a moon initiates the pattern, and the particles respond according to their orbits. The large-scale wave emerges from many small, individual motions. Observations since the late 20th century have revealed wave structures linked to several moons, including Mimas, Yanath, and Prometheus. Each moon creates a distinct pattern based on its orbit and distance from the rings. These waves act as traces that allow scientists to measure the properties of the rings, such as particle density and internal mass distribution. The study of ring waves provides insight into how gravitational interactions shape disk-like structures throughout the universe, including protoplanetary disks around young stars. The waves caused by Saturn's moons highlight the dynamic nature of the ring system. Although the rings appear calm from a distance, they contain continuous motion shaped by ongoing gravitational interactions. The patterns that form within them demonstrate how a planetary system organizes itself, creating a balance between order and motion that reflects the underlying physics of orbiting bodies. Saturn's rings appear bright and uniform from a distance, yet their surfaces evolve constantly due to impacts from micrometeoroids. These are small fragments of rock and dust that travel through the solar system. When they strike the rings, they alter the composition, brightness, and texture of the particles. Although each individual collision is small, the combined effect of countless impacts over long periods plays a major role in shaping the current appearance of the rings. Micrometeoroids originate from comets, asteroids, and other small bodies that shed material during their orbits. These fragments move at high speeds, often tens of kilometers per second. When they reach Saturn, they encounter the ring system, which presents a wide, thin target made mostly of water ice. The impacts release energy that breaks off tiny pieces of ice, distributes dust, and deposits darker material onto the ring particles. The accumulation of dark dust provides a key indicator of ring aging. Water ice reflects sunlight efficiently, but the addition of darker material reduces this reflectivity. This gradual change helps scientists estimate how long the rings have been exposed to micrometeoroid bombardment. If the rings were extremely old, they would contain significantly more darkening than currently observed. The relatively bright appearance suggests an age shorter than the age of Saturn itself. Impacts also modify the physical structure of the particles. Collisions chip away at their surfaces, creating rough textures or fragmenting larger pieces into smaller ones. This process affects how the particles scatter light. Smooth surfaces create sharper reflections, while rough or irregular surfaces produce a more diffuse appearance. Over time, continuous impacts lead to a mix of textures that contribute to the visual complexity of the rings. An everyday example can be seen in the erosion of painted surfaces exposed to blowing sand. Even small grains carried by wind eventually alter the surface, creating scratches and removing material. Saturn's rings undergo a similar form of erosion, though the process is driven by high-speed impacts rather than wind. Each micrometeoroid contributes to the gradual reshaping of the ring particles. Measurements from spacecraft during the late 20th century confirmed the importance of micrometeoroids. Instruments detected dust clouds forming at the moment of impact, as well as changes in the brightness of ring regions over time. These observations support the idea that the ring system experiences continuous external influence. The rate of bombardment helps define the long-term evolution of the rings, providing a timeline for how quickly they accumulate contaminants and lose material. Micrometeoroid impacts form a subtle but persistent force acting on Saturn's rings. They darken the surface, reshape particle structures, and contribute to the gradual thinning of the system. Although the impacts occur on a small scale, their cumulative effect reveals how active and dynamic the ring environment remains. The ongoing interaction between the rings and interplanetary material reflects the broader processes that shape planetary systems throughout the solar system. Saturn's rings create a range of visual effects because light interacts with their particles in distinct ways. The rings consist mainly of water ice, which reflects sunlight efficiently. Variations in particle size, shape, and distribution determine how much light is reflected, scattered, or absorbed. These interactions give each region of the rings its characteristic brightness and texture. Reflection forms the most noticeable effect. Smooth ice surfaces reflect sunlight in a clear and consistent way. When countless icy particles reflect light together, the rings appear bright, even from great distances. This collective reflection resembles the way a snow-covered field becomes strikingly visible under direct sunlight. The brightness depends on how clean the ice remains. Dark dust from micrometeoroid impacts can reduce the reflectivity by coating the surface of the particles. Scattering plays an equally important role. Smaller particles scatter light in many directions, creating a soft glow. Larger particles scatter light more strongly in specific directions, producing sharper highlights. The combined scattering from particles of many sizes generates the subtle gradients visible across the rings. These gradients help scientists identify variations in particle density and composition. Transmission occurs in regions where the rings are less dense. In the C ring, for example, sunlight can pass through the gaps between particles. The result is a semi-transparent appearance. Spacecraft images show shadows cast by the rings onto Saturn when the Sun sits at low angles relative to the ring plane. These shadows reveal how light travels through the thinner sections of the system, providing additional information about particle spacing and vertical thickness. An everyday analogy appears when light interacts with frosted glass or powdered snow. Smooth glass produces clear reflections, while frosted glass scatters light into a diffuse glow. Powdered snow behaves similarly, reflecting some light and scattering the rest. Saturn's rings combine these effects on a much larger scale, with each particle contributing to the overall visual result. The angle of sunlight also affects the appearance of the rings. During certain seasons, Saturn tilts in a way that allows sunlight to strike the rings at shallow angles. This makes the vertical thickness of the rings more visible and enhances shadows cast onto Saturn's atmosphere. The shifting illumination reveals structural changes and highlights features such as waves and gaps. Observations since the late 20th century have used these light interactions to map the rings with increasing precision. Instruments that measure reflected and scattered light provide estimates of particle composition, size distribution, and density. These measurements show that the rings behave as a dynamic optical system shaped by physical interactions between light and ice. The complex interplay of reflection, scattering, and transmission explains why Saturn's rings display such a wide range of visual behaviors. Their brightness, transparency, and gradients arise from the basic physics of light interacting with ice. The ring's appearance changes continually as Saturn orbits the Sun and as the distribution of particles evolves over time. Saturn's rings offer a clear example of how material behaves when it orbits a massive body, and this behavior reflects many of the same processes that shaped the early solar system. The rings consist of particles moving in organized paths that form a thin, stable disk. This configuration resembles the protoplanetary disk that once surrounded the young Sunday. Although the rings are far simpler than the disk that created the planets, they preserve physical principles that operate at both small and large scales. One of the most informative features of the rings is the way particles naturally settle into a flat plane. In the early solar system, dust and gas orbited the sun in a broad cloud. Collisions between particles gradually reduced their vertical motion. As energy dispersed through countless interactions, the material flattened into a disk. Saturn's rings show this same flattening process. Their particles move with small vertical deviations but remain tightly aligned with the ring plane. This reveals how gravity and repeated low-speed collisions guide material into ordered structures. The rings also demonstrate how regions of differing density form within a disk. In the early solar system, local variations in density help determine where planets would eventually grow. Higher density regions accumulated more material, while lower density regions remained sparse. Saturn's rings contain similar patterns. The B ring is dense and opaque, while the C ring contains fewer particles. These differences arise from gravitational interactions and the history of impacts, providing a smaller scale version of the variations that shaped planetary formation. Orbital resonances play a major role in organizing the rings, and the same principle influenced the formation of planets. When two bodies orbit in simple numerical ratios, their gravitational forces reinforce one another at regular intervals. In the rings, these resonances clear gaps, drive waves, and shape the distribution of particles. In the early solar system, resonances helped determine where planets could form stable orbits. They influenced the spacing of planets and contributed to the structure of the asteroid belt. Saturn's rings preserve this behavior in a form that can be observed directly. Accretion offers another parallel. In the protoplanetary disk, particles gradually stuck together during collisions, forming larger bodies that eventually became planets. Saturn's rings undergo limited accretion in regions where particle velocities are low enough for fragments to clump temporarily. Although these clumps rarely grow large due to tidal forces from Saturn, their formation shows how repeated collisions can lead to short-lived aggregates. These temporary clusters represent the early stages of the growth that once occurred on a much larger scale around the Sunday. An everyday comparison appears in the slow accumulation of snow during a calm snowfall. Small flakes land gently and stick together, forming larger patches. Areas with stronger wind patterns remain sparse, while calmer regions build thicker layers. The same general principles apply to a disk of particles orbiting a star or planet. Local conditions determine how material gathers and how structures evolve. Saturn's rings provide a scaled-down, accessible model of disk evolution. Their behavior demonstrates how gravity, collisions, density variations, and resonances shape the organization of orbiting material. By studying the rings, scientists gain insight into the processes that once governed the early solar system and led to the formation of planets. The rings stand as a present-day example of the physical rules that guide the development of larger cosmic structures. Saturn's rings respond directly to the gravitational environment around them, and this response allows scientists to study the forces shaping the system. Each particle follows an orbit determined by Saturn's gravity, the mass of nearby moons, and the collective interactions within the rings. By observing how the particles move, cluster, or shift over time, researchers gain insight into the underlying dynamics that govern planetary systems. One of the clearest examples appears in the spacing and motion of ring waves. These waves form when gravitational forces from Saturn's moons act on ring particles in a repeating pattern. The shape and frequency of the waves depend on the strength of the moon's pull and the distance between the moon and the ring region. By measuring these wave properties, scientists can estimate the mass of the moon and the density of the ring material. This method resembles determining the weight of an object by observing how it disturbs a surface of water. The rings also reveal how gravity varies across Saturn's environment. Regions of higher particle concentration produce measurable gravitational effects. Spacecraft traveling through the system detect slight changes in their trajectories as they pass over dense sections of the rings. These small shifts help map the distribution of mass within the rings. Similar techniques are used around Earth to measure variations in the planet's gravitational field. Resonances provide further insight into space dynamics. When a ring particle orbits in a simple numerical ratio with a moon, the repeated gravitational influence alters the particle's path. This process creates gaps, waves, and spirals that trace the structure of the gravitational field. By analyzing resonances, scientists can determine how gravitational interactions shape the long-term behavior of orbiting material. These interactions mirror the forces that influence asteroid belts and protoplanetary disks. An everyday analogy emerges from the motion of people walking on a flexible floor. When a group moves in rhythm, the floor oscillates in a specific pattern. The pattern reveals characteristics of the floor's structure, such as its stiffness and support points. Saturn's rings behave similarly. The coordinated motion of particles under gravitational influence reveals the stability and structure of the environment around Saturn. Spacecraft observations since the late 20th century have refined measurements of Saturn's gravity using the rings as natural instruments. As a spacecraft passes near the rings, small variations in ring density produce detectable changes in the spacecraft's speed. These changes offer precise estimates of Saturn's internal structure, including how mass is distributed beneath the planet's cloud layers. The rings act as a sensitive indicator, responding subtly to the gravitational forces at play. The behavior of Saturn's rings demonstrates how gravity shapes systems at many scales. Their waves, gaps, and density variations form a visible record of the forces acting on the system. By studying these patterns, scientists gain a deeper understanding of the dynamics that govern not only Saturn's rings, but also planetary systems, stellar disks, and other structures formed by orbiting material. Saturn's rings present a concentrated example of how ice behaves in space, and this behavior offers insight into environments where water may influence habitability. The rings consist primarily of water ice that remains stable under low temperatures and low pressure. Their structure shows how ice persists, evolves, and responds to external forces. And these patterns help scientists understand conditions that might support life elsewhere in the solar system. The brightness of the rings reveals how clean water ice reflects sunlight. Pure ice scatters light efficiently, creating the pale tone visible from afar. This efficiency explains why icy bodies in the outer solar system remain visible even at great distances. Saturn's rings show how ice behaves when constantly exposed to micrometeoroids, radiation, and gravitational forces. The erosion and redistribution of material help researchers model similar processes on moons such as Enceladus and Europa. The rings also demonstrate how ice interacts with temperature changes. Although the particles remain frozen, their surfaces shift subtly as they absorb and release heat. These fluctuations influence how the particles reflect light and how they bind together during low-velocity collisions. The stability of the rings under extreme cold provides a reference for understanding the thermal behavior of ice-rich environments around other planets. Water ice acts as a reservoir of information about chemistry in the outer solar system. Spacecraft studies show that the ring particles contain only trace amounts of organic material. This suggests that the rings formed from relatively pure sources, such as the breakup of an icy moon or a captured object. Comparing these findings with measurements from icy moons helps identify where organic molecules may accumulate and where they remain scarce. An everyday comparison can be found in the behavior of ice during a long winter. Snow accumulates, becomes compacted, and gradually changes texture under repeated weather conditions. The ice in Saturn's rings experiences a similar evolution, though driven by impacts and radiation rather than temperature cycles. Each particle records a history of small alterations, helping researchers track how ice transforms over time. Insights from the rings extend to the study of habitability. Moons with subsurface oceans rely on thick layers of ice to insulate liquid water. By examining how ice responds to external forces in the rings, scientists refine models of how ice shells behave around potential habitats. Understanding grain size, reflectivity, and thermal properties helps constrain the conditions required for stable environments beneath icy surfaces. The study of Saturn's rings offers a focused way to observe the physics of ice in space. Their behavior under constant bombardment, extreme cold, and gravitational shaping provides a framework for interpreting environments where water plays a central role. These lessons contribute to the broader effort to understand which regions of the solar system may support the chemical and physical conditions necessary for life. Saturn's moons and rings exist in a continuous exchange of gravitational influence. Each moon interacts with the ring particles through its orbit, and the rings respond by forming waves, gaps, and boundaries. At the same time, material from the rings can affect the surfaces and orbital behavior of nearby moons. This relationship reflects a broader pattern seen in planetary systems, where large and small bodies evolve together. One of the clearest examples of this interaction appears near the edges of the rings. Shepherd moons, which orbit close to the ring boundaries, help maintain the sharp edges of certain ring regions. Their gravitational pull nudges particles back into place, preventing them from drifting outward or inward. The process resembles a small object guiding loose grains into a narrow path. Without these moons, some ring sections would slowly spread out and lose their defined structure. Moons located farther from the rings influence them through orbital resonances. When a moon orbits Saturn in a pattern that repeats with the motion of ring particles, its gravitational pull occurs at the same point during each cycle. Over long periods, these repeated interactions clear gaps or create waves in the ring material. The Cassini division is one of the most prominent examples of this process. Smaller moons generate subtle waves that trace the underlying structure of Saturn's gravitational field. The exchange also operates in the opposite direction. Some moons collect material from the rings through gentle impacts or electrostatic interactions. E-ring particles, for instance, originate largely from the geysers on Enceladus and form a wide halo around Saturn. In turn, ring particles occasionally settle onto the surfaces of small moons, creating bright or dark patches depending on the composition of the incoming material. These deposits provide clues about the direction and speed of particle movement. Tidal forces contribute further to the evolution of both the rings and the moons. As a moon travels through Saturn's gravitational field, internal friction can heat its interior. Enceladus displays this effect through active geysers that eject water ice into space. Some of this material enters Saturn's ring system, linking the moon's internal processes with the broader environment. The rings themselves experience tidal shaping that maintains their thin form and prevents large-scale clumping. An everyday comparison appears in the way ocean tides respond to the gravitational pull of the moon on Earth. The tides shift the distribution of water, and the Earth's rotation gradually affects the moon's orbit. Saturn's rings and moons follow a similar exchange. The forces act on different materials and scales, but the reciprocal influence remains a defining feature. Observations since the late 20th century have revealed the extent of this dynamic relationship. Changes in ring waves, moon orbits, and particle distribution reflect ongoing interactions that unfold over long time scales. The moons and rings form a coupled system where each component shapes the behavior and evolution of the other. This interdependence provides insight into how gravitational forces structure planetary systems across the solar system and beyond. Saturn's rings function as a detailed model for studying how disks behave in space. Their structure, motion, and long-term evolution reflect the same physical principles that operate in much larger systems, such as protoplanetary disks around young stars or debris disks formed after planetary collisions. Because the rings are close enough to observe directly, they provide a clear window into processes that often occur on scales too distant or obscure to measure with precision. One of the most important features of the rings is their thin, organized shape. Countless particles follow predictable orbits that form a narrow disk only a few tens of meters thick in most regions. This arrangement demonstrates how material naturally settles into a flat plane under the combined effects of gravity and collisions. In young stellar systems, the same process shapes the disks that eventually give rise to planets, moons, and smaller bodies. The rings also show how waves and patterns emerge within a disk. Gravitational interactions with Saturn's moons create spirals, gaps, and oscillations that travel through the ring material. These structures resemble the density waves observed in protoplanetary disks, where forming planets carve out paths and create repeating patterns in the surrounding gas and dust. Saturn's rings reveal these behaviors in a form that scientists can monitor over time. Another parallel appears in how particles interact. Collisions within the rings occur frequently, but at low speeds, leading to gradual changes in size, shape, and distribution. This environment mirrors the early stages of growth in planet-forming disks, where small fragments begin to stick together. Although Saturn's rings do not produce large bodies due to Saturn's strong tidal forces, basic physics of aggregation remains visible. The rings also act as a test bed for studying viscosity in disk systems. Viscosity describes how material spreads or resists spreading over time. In Saturn's rings, viscosity arises from the combined effects of particle collisions and gravitational interactions. Measuring how quickly ring material moves or diffuses allows scientists to refine models used to describe much larger disk systems where gas and dust respond to similar forces. An everyday comparison can be made to observing how grains of sand behave when poured onto a rotating surface. The grains migrate, form patterns, and settle into stable regions depending on the speed of rotation and the flow of the material. Saturn's rings demonstrate these behaviors within a real astronomical system where the forces involved operate with extreme precision. Spacecraft observations since the late 20th century have transformed the rings from a visual curiosity into a framework for understanding disks across the universe. By tracking how ring structures evolve, how waves form and dissipate, and how particles interact, scientists can test theories that explain the behavior of much larger and more complex systems. Saturn's rings provide a close-range, continuously changing example of how orbiting material organizes itself under the influence of gravity and motion. Saturn's rings appear stable from a distance, yet they undergo continuous changes that gradually reduce their mass. These changes indicate that the rings will not remain in their present form indefinitely. Over long timescales, the rings lose material through several processes, and this slow loss shapes predictions about their eventual disappearance. One of the main forces on the rings is a phenomenon known as ring rain. Particles within the inner regions of the rings experience drag from Saturn's upper atmosphere and interactions with the planet's magnetic field. These interactions cause charged particles and small grains to drift inward. As they fall towards Saturn, they enter the upper atmosphere and disintegrate. Measurements from spacecraft in the late 20th and early 21st century showed that material leaves the rings at a measurable rate, suggesting that the rings are gradually thinning. Micrometeoroid impacts contribute further to this loss. Each impact releases small fragments that either drift away from the rings or become part of a diffuse cloud that eventually disperses. Impacts also darken the rings by depositing dust, reducing their reflectivity over time. This darkening makes the rings more susceptible to heating, which can alter their structure and accelerate the redistribution of material. Tidal forces influence the long-term stability of the rings as well. Saturn's strong gravity prevents particles from clumping into larger bodies. As a result, the ring material remains as individual fragments rather than forming new moons. Without the ability to grow into larger structures, the particles remain exposed to processes that erode them. Over millions of years, the balance between tidal forces and erosion shifts, leading to a gradual decline in ring mass. An everyday comparison can be found in the wearing away of river ice at the end of winter. Even without a single dramatic event, sunlight, water currents, and wind slowly weaken the ice until it thins and breaks apart. Saturn's rings experience a similar slow deterioration driven by multiple influences. The changes occur too gradually to observe directly over short periods, yet long-term measurements reveal the cumulative effect. Estimates of the ring's future vary. but many models suggest they may disappear within tens to hundreds of millions of years. The exact timeline depends on the rate of ring rain, the frequency of micrometeoroid impacts, and the influence of Saturn's magnetic field. As material continues to fall toward the planet, the inner rings will fade first. Over time, the outer rings will also thin until the entire structure dwindles to a faint remnant. The projected disappearance of Saturn's rings provides insight into the life cycle of disk systems. Just as disks form, evolve, and disperse around young stars, Saturn's rings follow a similar arc on a smaller scale. Their gradual decline reflects the natural processes that govern orbiting material throughout the solar system. The rings present a moment in time within a longer evolutionary sequence, illustrating how structures shaped by gravity eventually transform and fade. Planetary rings exist around several worlds in the solar system, yet Saturn's rings remain the most extensive and reflective. Comparing them with the rings of Jupiter, Uranus, and Neptune highlights the differences that arise from composition, density, and the gravitational environment. These comparisons show how diverse ring systems can be, even though they follow the same fundamental physical principles. Jupiter's rings form one of the faintest systems. They consist mainly of fine dust released from small moons struck by micrometeoroids. Because dust grains absorb more light than they reflect, Jupiter's rings appear dark and difficult to observe. Their low density allows light to pass through with minimal scattering. The system contains no dense regions like Saturn's B ring. Instead, it forms a thin halo that demonstrates how ring systems can develop even around a planet with strong gravity and active moons. Uranus presents a different type of ring system. Its rings are narrow and sharply defined, with dark material that reflects only a small amount of sunlight. These rings contain larger particles than those found around Jupiter, yet remain far less dense than Saturn's. Shepherd moons help maintain their crisp edges. The ring's dark appearance suggests the presence of carbon-rich material, possibly originating from ancient collisions or surface processes on Uranus's moons. Neptune's rings resemble those of Uranus, but include a distinctive feature: bright arcs. These arcs appear as clusters of ring material that remain confined to specific regions, even though orbital motion tends to spread particles evenly. Gravitational interactions with nearby moons help sustain the arcs, creating a pattern that differs from the continuous bands seen around Saturn. Neptune's rings are also darker and contain more dust, giving them a subdued appearance. A comparison to everyday situations can clarify these differences. The rings around Saturn resemble a broad sheet of ice that reflects sunlight clearly. Jupiter's rings function more like a faint cloud of smoke, while the rings of Uranus and Neptune resemble thin, darkened bands of powdered material. Each system displays unique visual characteristics based on particle composition and density. Despite their differences, all ring systems share similar processes. Micrometeoroid impacts shape their structure, moons influence their stability, and gravitational interactions organize the particles into distinct patterns. These shared behaviors reveal the universal physics that governs disk systems throughout the solar system. The comparison emphasizes what makes Saturn's rings unusual: their high concentration of water ice, wide extent, and reflective surfaces set them apart. At the same time, the other ring systems show how varied planetary rings can become when shaped by different environments and histories. Studying these systems together offers insight into the range of structures that orbiting material can form and the physical rules that guide their evolution. Saturn's rings preserve physical conditions that resemble those present during the early stages of the solar system. Although the rings themselves may not date back to that era, their structure and behavior reflect the same principles that shaped the environment where planets and moons formed. Studying the rings provides insight into how dust, ice, and rock once moved, gathered, and evolved around the young Sunday. One of the most informative aspects of the rings is their disc-like shape. In the early solar system, gas and solid particles orbited the Sun within a broad disk. Repeated collisions reduced their vertical motion and caused the material to flatten into a plane. Saturn's rings show this same tendency. Their particles remain aligned with the ring plane because gravity and low-speed impacts continually remove excess vertical movement. This behavior reflects the natural process by which protoplanetary disks became thin enough to support planet formation. The rings also demonstrate how local variations in density arise within a disk. In the early solar system, these variations created regions where solid bodies accumulated more rapidly. Saturn's B ring and its contrast with the thinner A and C rings illustrate how gravitational interactions and particle distribution produce zones of differing density. These zones provide a way to study how similar variations may have guided the growth of planets and smaller bodies. Wave patterns within the rings offer further parallels. Density waves generated by Saturn's moons resemble the spiral waves seen in protoplanetary disks, where forming planets disturb the surrounding gas and dust. The rings allow these interactions to be observed in real time. The waves reveal information about mass distribution, orbital motion, and the strength of gravitational disturbances properties that would have shaped the early solar system on a much larger scale. The diversity of particle sizes in the rings also mirrors the early stages of planetary growth. Small grains continually collide, break apart, and reform. This dynamic environment reflects the competition between accretion and fragmentation that determined whether early solid bodies grew or eroded. In Saturn's rings, tidal forces prevent large-scale growth, but the basic physical processes remain visible and measurable. An everyday analogy appears in the behavior of sediment carried by flowing water. As the water slows, particles settle into layers and patterns emerge based on grain size and current strength. Saturn's rings show how similar organization occurs in an orbiting system where gravity and motion replace water flow. The structure that develops highlights how disks evolve into ordered configurations. Observations collected since the late 20th century provide evidence that the conditions seen in Saturn's rings match many of the models used to describe the early solar system. By examining how particles cluster, how waves propagate, and how density changes across the rings, scientists refine their understanding of the processes that guided the formation of planets. Saturn's rings function as a scaled, accessible example of the forces that shaped the solar system during its earliest stages. The rings around Saturn offer a nearby reference point for understanding the much larger and more distant disks observed around exoplanets. Although current instruments cannot yet reveal the fine details of exoplanetary rings, the behavior of Saturn's system helps interpret the structures detected around distant worlds. These comparisons show how ring-like formations arise, evolve, and interact with their environments far beyond the solar system. Some exoplanets appear to host disk that are far larger than any ring system found around the giant planets in our neighborhood. Observations of young, massive planets have revealed extended halos of dust and ice that stretch millions of kilometers. These structures resemble scaled-up versions of Saturn's rings, with material orbiting a central body in a stable, flattened arrangement. The presence of these disks suggests that ring formation is a common outcome when large bodies accumulate material during or after their formation. In certain cases, gaps or irregularities appear in the disks around exoplanets. These features echo the patterns seen in Saturn's rings, where gravitational interactions with moons create divisions, waves, and confined regions. The exoplanetary gaps may indicate the presence of orbiting bodies too small or too distant to detect directly. The physics remains consistent. Any object with enough mass can disturb the disk around it, reshaping the surrounding material. The composition of exoplanetary disks varies depending on temperature and distance from the host star. Cooler regions favor the presence of ice, while warmer zones produce silicates and other rocky materials. Saturn's rings provide an example of how ice-dominated systems behave. By studying their reflectivity, density distribution, and long-term evolution, scientists refine models used to interpret observations of distant disks where the specific composition is more difficult to determine. An everyday analogy can help visualize this process. Consider flowers spread across a rotating plate. If small objects are placed on the plate, they carve paths and create patterns within the material. The same general behavior occurs in exoplanetary disks. Gravity, orbital motion, and local disturbances work together to form structures that vary in thickness, brightness, and shape. The scale of exoplanetary disks highlights how ring systems can evolve over time. Some young planets possess disks so large that they may eventually form moons. This process mirrors the early history of the solar system, when a disk of material around Earth led to the formation of the moon. Saturn's rings do not produce moons today because of Saturn's strong tidal forces, but the same physical rules apply across different environments and time periods. Observations collected since the late 20th century have shown that disk-like structures exist throughout the galaxy. Saturn's rings serve as a local example that helps interpret these distant systems. The dynamics of orbiting material, its distribution, disturbances, and gradual evolution remain consistent across extreme differences in scale. By studying Saturn, researchers gain a framework for understanding how ring systems form and develop around worlds far beyond the reach of direct exploration. The appeal of Saturn's rings comes from a combination of structure, scale, and clarity that aligns with the way humans perceive order in the natural world. The rings form a pattern that is both complex and highly organized, creating a visual balance that feels familiar despite its extraterrestrial nature. Their symmetry, brightness, and gentle curvature evoke responses shaped by how the human brain processes shape and light. One contributing factor is the ring's geometric simplicity. They create a clear, continuous band that encircles the planet with remarkable precision. This consistency mirrors patterns seen in natural formations on Earth, such as ripples on calm water or layers of sediment arranged by wind. The mind recognizes these repeating structures and interprets them as stable and harmonious. Saturn's rings extend this pattern across a scale far larger than anything found on Earth, reinforcing their impression of order. Brightness also plays a role. The high reflectivity of the icy particles creates a sharp contrast against the darker background of space and the muted tones of Saturn's atmosphere. Humans are naturally drawn to scenes where light and shadow interact in clean, well-defined shapes. The rings offer a continuous surface where sunlight scatters gently, producing a soft gradient that remains visually distinct, even from great distances. The thinness of the rings adds to their appeal. Observing such a wide structure that remains only a few tens of meters thick challenges everyday expectations about size and proportion. The contrast between their vast horizontal span and minimal vertical depth creates a sense of delicacy that seems unlikely for a structure composed of countless orbiting fragments. This contrast resembles the appeal of finely crafted objects that appear lighter than their true mass. An everyday analogy appears in architectural designs that combine large, open forms with precise lines. Bridges, domes, and curved walkways often create a similar response by balancing strength with graceful geometry. Saturn's rings display this balance on a planetary scale, offering a structure that is both robust in its orbital mechanics and delicate in its physical appearance. Movement enhances the visual effect. The rings consist of particles traveling at high speeds in coordinated orbits. Although the motion cannot be seen directly from Earth, spacecraft observations reveal shifting shadows, waves, and patterns that change with Saturn's seasons. These gradual variations give the rings a sense of continuity and evolution, reflecting the passage of time without disrupting their overall structure. The perception of Saturn's rings also reflects an appreciation for clarity in the midst of vastness. Space often appears empty and diffuse, yet the rings offer a clearly defined shape that stands out within the surrounding environment. Their presence provides a reference point that makes the scale of the solar system feel more accessible. The rings act as a bridge between the familiar and the immense, giving viewers a structure they can understand while still conveying the vastness of the cosmic setting. Humans find Saturn's rings beautiful because they embody patterns that resonate with the way perception organizes light, shape, and motion. Their symmetry, contrast, and delicate proportions present a rare combination of qualities. These traits create a visual experience that feels both orderly and expansive, connecting human perception with the broader structures of the universe.